Hi, thank you for coming today. We are Team MuEpsilon. We're working on the Aurasen project. To my right is Mark Davenport, Mark Phillips, Justin Mueller, and I am Daniel Young, and this is our mid-semester presentation. All right. So here's a little background on the problem. Essentially, Americans are living longer and longer these days, and we're also increasingly more lively in our older age. And the baby boomers, God bless them for inventing rock and roll, are also paying for it in spades because of the rock concert. Long story short, more and more of us are needing the finely tuned expertise of an audiologist. The problem with that is that audiologists are hard to come by, and they're becoming harder and harder to produce. 18 states have already raised the bar to at least a master's degree, and doctorate degrees are becoming more and more prevalent as the basic prerequisite to get into this. What does that mean? It means that the demand for audiologists is already outpacing and will continue to outpace the supply. So what do we do about this? Well, foreseeing a potentially massive market, a small startup company named Aurasen designed an idea that would allow them to put programmable hearing aids into every home at an affordable price. This three-part project consists of a software team that you heard from earlier, who are responsible for producing the program that runs on the home Windows-based operating system that allows them to tune the hearing aids. An internal hardware team, which is responsible for designing the specific circuits, components, electronics, and things like that implicit in the system. And also us, the external hardware team, who are designing the external enclosures, couplers, plugs, and the like. So, even external hardware in and of itself is a four-tiered approach. We have four different aspects of our project. First is the ASP enclosure. That is the programming box that's going to sit outside of your computer on the desk. You'll plug it in, and you also hook your hearing aids into it. Here's the objective tree for it. You can see the red lines are constraints, and the green lines are objectives. You'll see this right here. The safety will be highlighted red in every single one because we want safety to be a paramount objective, a constraint in all of these. We want them all to be durable. So you can see if you're 1,000 cycles per use, that spells out to about 5 years of 5 years of use. Okay, the other one, next one up is the hearing aid housing. Basically, we need to modify existing hearing aids to accept the new system. The objectives for those is, of course, durability. You see again, obviously it's got to protect the internal hardware. It's going to be easy to use, ergonomic. You'll see here max overlayer and induction, which are specific. They're actually not in market, not in the market right now. We'll get into that later. And of course, safety and patents as well. Third component is a magnetic coupler. This was you're going to be able to program your hearing aids at home. So what happens is you can do this with a few projects, with a few products out there right now, but plugging the hearing aid into the data cable and program it is atrocious. It's like trying to thread a needle that got run over by a car with a piece of paper. So it's a big problem, especially if you're old. I don't even have steady hands and I'm 27, so I can imagine by the time I get this old, I'll be like, so what this is going to do is this is going to allow us to use magnets to make plugging your program in very easy. So here you see provides physical connections, self-aligning. They're going to be polarized so that you can't plug the left programming cable into the right hearing aid. And also we're going to use an inductor to transmit the data, and we'll get into that in a second. And finally, the last aspect that we're working on is a carrying case. Basically something that you can put the entire system into, and it'll be what you see when you first unwrap the product. Obviously, we've received a few constraints from the customer. They would like a stamped aluminum exterior so that it's got a real good professional sturdy look. They also noted that they wanted us to use a molded foam interior, so when you open it up, there'll be little cutouts recessed to help organize everything. So we're looking for a very top-notch professional, even medical style appearance. And obviously any applicable legal and engineering standards. We want to follow those as well. So moving on, let's get into the engineering requirements for each of these. So this is our second draft for the ASP enclosure. We printed this one. It's actually right here if you want to see it in real life. And so the engineering requirements for this particular device is, obviously, it's got to house all the internal hardware, so all the circuit boards, speakers, things like that. It has holes for speakers, 2 speakers spaced appropriately to provide adequate stereo sound. It also needs to have holes for your data connections. Obviously, this thing's got to plug into something, so there's got to be a hole for that. And it's got to be relatively rigid. If someone knocks it off the countertop, we want this thing to survive. And we also want what's inside to survive. So here is the magnetic coupler. This is, again, just facilitates the insertion of the programming cable into the hearing aid itself. We know it needs to be polarized. So again, you can't plug the wrong hearing aid programmer into the wrong hearing aid. It needs to use an inductor to transmit data, so there actually isn't a physical connection like, say, a USB cable or a power cord when you plug into the wall. It's actually wireless, but over a very, very short distance using a magnetic field. And it needs to be sturdy as well, and it needs to be easy to handle. So this is actually a cross-section of it right here. You can see the coil for the inductor. This is the core and the outer housing. These would be cables that the data comes through. We'll get into that later. And in the hearing aid housing, it's essentially just copying an existing housing that was given to us. This is a rough, it's an unfinished model that Justin drew up for us. The major modification here is that it has to accept the female end of the magnetic coupler. So however the male end looks like an end of a data cable, this one has to be able to receive it. And it also has to have the other polarized magnet so that you can't, again, plug the wrong cable into the right hearing aid. And finally, the carrying case, it needs to protect everything, hold it in place, and provide a very top-notch professional appearance. And so I'm going to hand it off to Phil.
So as far as standards, we are continuing in our research, regarding standards. In particular, we took a look at the mill standard that was given by our client. What we found out is that where it doesn't really talk about like the stereo effect, like spacing, because Dan wanted us to look at the spacing. It does talk about like if a person is in, say a room, workers in a room, how far from a loudspeaker, for how long. It's basically like OSHA requirements, it's safety. So we didn't really find anything there, but we are continuing on that. Having said that, and while we understand how important standards are and codes are, we also have the clinical trials, so we temporarily shifted our focus to the prototype in order to make sure that we were keeping our end up for the rest of the teams. So in terms of concept generation and selection, this is the morph chart that we used, and you can see the highlighted areas, which are actually selections. They were selected using a metrics chart, which I'll show you in a second. We're currently using that metric chart for our prototyping now. I'll get to that more later. So this was, we were able to pull out some, we pulled out some function and means from the objective tree. And that's how we were able to populate this. Now, something to realize is that a lot of the selections that we made were actually given by the client. So there wasn't, too much leeway and too much grading, when it came to that. So some of these, we were just thinking of, how we could expand the design space for the sake of the I have to apologize. I am not feeling well, so I'm losing my train of thought. It was for the assignment.
It's like learning experience.
Thank you. So again, here's the ASP housing and the first prototype. This is the grading sheet that we used in the metrics. So as an example, the top one, we gave it a 7.5. This should protect internal hardware from impact. This is kind of hard for us to do because we don't want to break it yet because we just printed it out, so we haven't tested it. So this is our opinion of how well it'll hold up. But this is just an example of how we're using this grading sheet to grade our prototype so that we can do that iterative process. Here's a couple more examples. It should allow for data cable access. It does that, so it got 100. Another example is should allow for notification lights. Right now we noticed that there aren't any lights that are in the design, so we graded it low. And this is all just showing how we use the grading sheet in order to impact our prototype designs. And so regarding the hearing aid housing, this is the same process. Just a couple things to point out is that we're basically copying new sound for these two functions. And again, here's kind of showing how we're copying it. And then our grading sheet. So something that's very important, Dan touched on it, is that the magnets, the inductors, are polarized. So we've got basically a positive that will be embedded in one side and the negative in the other. That way they can't be confused. They actually won't connect. So that's the idea right now. And this is an example of some of the inductors that we made. So this is two that are coupled, and these have the same number of turns. This is strictly for prototyping. We were working with the internal hardware and just trying to get this created. You can barely see a little bit that it's colored red, just so that we can keep track of the poles for if we ever embedded it or anything like that, we wouldn't lose track of it. And then again, our grading sheet. And right now, the inductive data transfer is at a 1, just because we're getting all the kinks worked out. And then the carrying case. And as Dan mentioned before, it needs to compartmentalize everything and have multi-film packing and things like that. So continuing on is my technical.
So now that you have an idea of what it is that we set out to design, this is sort of where the rubber meets the road. So the design, analysis, and optimization is an iterative process that basically brings the best ideas forward. And this is where math, physics, and modeling, all of that come into play. You can see here, you start with an idea, and you take it, you say, what do I like about this? What needs to improve about this? And you improve it with each successive iteration until you get a product that you and your client are both happy with. So now this is by no means comprehensive, but these are some of the important parameters that we considered in our design, analysis, and optimization. And these include the physical modeling, which has been a huge part of our project because the nature of it is external hardware. So there's 3 major components that we're sitting down on SolidWorks and modeling all the time. Something that follows closely with that is the geometric optimization of each part, which involves all the dimensioning and tolerancing, and basically making everything fit. With that, we also have mathematical modeling that we're currently working on right now with the magnetic coupler, basically calculating the magnet strength. There's also thermal analysis that goes into this, and also stress analysis. So let me touch on a few of these just briefly. Now the modeling, as I said before, is a huge part of what we've been doing, and we've sort of split up the duties as to who's modeling what. So I've been handling the ASP enclosure, the AurasenMuEpsilon platform, which is here, what you've seen before. The magnetic coupler has been divvied up between Mark Phillips and Dan Young. We sort of separated this into 2 components as well, because there's the inside part, the inductive part, and the magnet, which is also, a lot of that is with the internal hardware team. And also there's this sort of outer casing or shell that needs to be considered. Also the hearing aid housing, my man Justin Mueller has been spearheading that. And a lot of these have gone through a lot of iterations, and we'll talk a little bit more about that later. So here, like I said before, the geometric optimization is really huge because a lot of this is physical parts. Does this fit? Does this connector go in the right place? Does the PCB mount properly? All of these are design considerations that we've had to wrestle with a lot in this process. So the thermal analysis, we touched on this last semester, but after an ongoing conversation with our internal hardware team, it was determined that the amounts of power we're dealing with here are pretty much negligible as far as heat transfer. So because we're using USB power, we're talking less than 5 watts of power draw. which, to put that in perspective, that's 5 watts is about what your cell phone draws when it's charging. So we're not worried about heat transfer in the ASP enclosure. So heat sinks, which we anticipated having to design, and ventilations are unnecessary. So we decided we don't want to over-engineer this, and we moved on. Also, the mathematical modeling goes into play with the force of the magnetic couplers. Basically, we have a lot of tiny magnets that we've sort of been playing with, and we thought the best way to determine the magnet strength would be to hold all of these in our hands and connect all of them and see, well, does this feel good? Is it too strong? Otherwise, you look at 5 newtons or 1 newton. How do you know if that's too strong or not? So from that, we're going to determine the force that we need to deal with and whether we're going to go for a sort of ring design on the magnet or just a cylinder design. And from that, we'll be able to model in MATLAB using the right equations our sort of design space and what inner radius and outer radius we want to use for the ring design. So now the ASP enclosure, like you've heard before, I was privileged to be able to model this, and I've been working on it a lot. Now we've come up with 3 iterations at this point. See the first iteration. It's very basic, not a lot of the main features that we want there yet. The second iteration, as you see here, we move forward a lot with speaker holes and mounts, all that stuff. That we actually have here. We printed it out on our 3D printer, and it's very basic. It's got the speaker mounts. It's got mounting bosses on the bottom. There is a bottom piece that we didn't bring, and we like it. This design is something we discussed with our clients, the sort of wedge design. And this was cool for us because you don't really know how something feels or looks on the computer screen, so this gives us a good idea of how big it actually is. And of course, this isn't our final design. I'm stepping on the toes of Justin when he talks about prototyping, but this sort of goes hand in hand with the prototyping process. The next iteration is something that we have right now that we haven't printed yet, and this allows for the correct connectors, which are 2 S-video cords and a mini USB-C right here, as well as the speaker mounts, of course, a little bit of a different trapezoidal design that we thought would be more aesthetically pleasing, and is also more space efficient, and that's something that goes with the geometric optimizations. Can we make this fit better? Can we make it more compact? Can we reduce our shipping costs when it comes to manufacturing? Now Justin is going to tell you about the modeling of the magnetic coupler.
Thank you, Mr. Davenport. All right, the mag coupler so far it has gone through several iterations or designs as well, as Mark showed you for the ASP enclosure. The mag coupler, some of the things that we've dealt with is the orientation of the wire, whether it's going to be straight or curved. And a new development that we've made is to make the mag coupler case 2-piece, so it'd make ease for the injection molding process. As you see there, there's ample room for the magnet size and wrapped with wire that we're dealing with, as well as a hole at the top to allow for data transfer. As far as the hearing aid housing goes, it's also got through several iterations. This picture that you've seen many times was based off the original New Sound model, just by a picture, because we had to send it into China for a while, but it stayed fairly accurate. The printed model was made larger intentionally to allow for room to mess with different size magnets to test the magnetic strength. We wanted to make sure that the magnets were strong enough to stay connected with that appropriate amount of movement. Like, nobody's going to be a robot and stay still for how many hours this takes. And we also wanted to make sure that this was not too strong, so that ideally that you can disconnect it with one hand, but if that is too hard to do, we'll make a compromise of 2 hands, but it is much easier than the former method of having to find the little holes to plug into. So that's our goal for progress with hearing aid housing. Now to transition into the prototyping process of the 3 main components. For the ASP housing, the main goals that we strived for was to make sure that I had ample spacing for the speakers, as well as the circuit boards provided by the internal hardware design team. And we also wanted to account for optimal user interaction, such as having the speakers be distance apart, as well as at a good angle for good acoustic environment. So at first, we took a recommendation from our client to do the expanding foam. However, the brand that we got from Home Depot didn't work as good as we planned, but there are good foams out there. But we didn't have time to use that because we had a fine and dandy 3D printer that could serve our purposes. So we decided to be proactive and move on to that. So as Mark already showed you, that's the printed ASP enclosure. You can see the speakers fit nice. There's enough room for the circuit board. Now for the mag couplers, some sample pictures from magnetic connections online that you can find, as well as an inductor. The main goal that we tried to aspire for the mag coupler is to make sure that it can facilitate data transfer as well as have appropriate magnetic strength. And I already said, strong enough to not get detached and not too strong so that you can disconnect it with ease, especially for the elderly who might have trouble with some of the stronger strings out there for magnets. So as we already went over, there's the most recent model, but we're continually iterating to make sure we can have this ready by the beta testing stage. As you can see up there, there is a magnet coil that we helped wrap with, much thanks to the internal hardware team for helping us out with that. So that's where we are with that. Okay. For the hearing aid, here's the model that Newsan gave us. That's what it was based off of. And as you can see there, that's how the current hearing aid parts fit into that. As we approach the beta testing stage, we'll make the prototype as close to the same size as possible while including the magnetic inductor, which shouldn't be a problem. So as you see, these are the early iterations that we dealt with, and as of today, this is where our 3 stages stand, but we're once again continually iterating towards the beta testing stage. Moving on, here's our budget. We have a 3-tiered budget. This is what, if we're going to actually develop the team out there, of course we require hours for pay, the parts initial prototype, as well as testing of the final product. This is our sample budget if we demanded to pay, but as a senior project, so of course it's courtesy. Here's a printed 3D prototype, so that would be the price. As far as we know so far, it's seemingly provided complimentary by CP School of Engineering. So for that, we would thank you, CP School of Engineering, as well as the parts that we have not gone to yet. This is our budget where it stands today, the parts that we bought from Home Depot for the foam, and as well as the magnets that we use, as well as tax and shipping. Only $27 so far, really thrifty. Here's our work breakdown structure at a glance. Gonna zoom in. First semester went great. We did all the pretty sure all the documentation that was required about the design notebook, building and modeling, alpha testing, beta testing. So this semester we're focusing on getting ready for the beta testing stage on March 21st on Wednesday, as well as having all the bi-weekly progress reports and all the presentations that we've done so far. These are beta times. So that concludes it. And there's work breakdown structure, same thing. You've seen this a million times. There's a task everybody has over there. There's a condensed version.
All right, any questions?
You gave a grade of 1 for data transfer. Are you modeling that? You've learned quite a bit about modeling the magnetic. How about modeling the
We'll look at the hardware on that. So we were in the process of actually making the inductors for them, just to get them, basically just how do we glue it, because they're very small. So the process is how do we glue it together, how do we get it together, and then we hand it off. And the reason why we put a 1 is because the last thing we heard is that something wasn't working right.
It wasn't coupling.
Yeah.
Okay, well, so really what you're saying is you're having the
Which could also be different
internal
to
hardware people do the checking.
Well, they're seeing if it'll pass the data.
Yes, that's what I mean.
Yeah.
For deducting
Yeah.
data transfer.
Yeah.
On that, have you looked at the frequency limits of doing your data pulses on the magnetic, building a magnetic coupling? When people do magnetic coupling, it's usually 60 hertz for low frequencies. And there's a frequency limit on how fast you can do stuff in that inductive coupling system.
Yeah, that's really outside the scope of, our involvement in those internal hardware that was designing the number of turns and everything. Okay. So we were purely manufacturing.
Okay. Well, yeah. Got to feed them that message I just gave you. Go back to the very beginning on Daniel. Daniel's stuff right at the beginning. Yeah. I got a little seasick, but go all the way back.
All right.
Those slides right there is a good one. The next one. Yeah, take one of those. There's several slides up there, actually that one is, but there's several slides where you've got this great title, and there's a lot of good stuff in here, guys, I just want to raise it up a little more notch. You got great titles, and you got great pictures, and then when we end up wanting to do at that point, you have no warrants. So if you go back to the Michael Alley technique, you have the assertion titles, you have pictures, but then you don't have the things that you really want to, then you start saying things that go with each of those pictures, but there's nothing on there to tell us what those pictures are telling. Does that make sense?
Are you saying text on the screen? Or-
Yes, a small amount of text with the pictures. He calls it warrants, if you look it up in this process. You're making an assertion, and then you have warrants. It's like a legal term, right? And those warrants go with the pictures. So there were several of them. I got lost, especially as it was turning, and you were making points. I couldn't follow your points with what your pictures were. And it happened a bunch of the beginning. So if you go back as an example, I think it was right at the beginning, when you were doing stuff, all the way to the beginning. Yeah, those right there. So, engineering requirements for the carrying case. And you said what the requirements were, and they were really short and succinct, and there's no reason you just could put those as bullets. Why that case? You understand what I'm saying?
Right, I was.
Like, what are the requirements?
I was extremely hesitant to put any unnecessary text on the screen that I couldn't communicate verbally. I misunderstood.
Yeah, yeah. But if it's that short and it's your points, you can have it flash up there and flash off. Because it was spinning and moving from slide to slide, and then you say your points, and then I just couldn't follow it. I'm just letting you know. So go back to the previous one. A couple more. The case is one with just one picture.
You can see the objective tree? Like this one?
Yeah, like that. Well, that was, it would have been nice to know what an ASP enclosure is from a picture standpoint there, but that's okay. I'm not. There was another one like the, going back. I'll go through your handout. Okay, fine for you. But it just was going so fast, and you were saying things that were critical for me to understand as an audience that was not on the slide.
Okay.
Okay.
Well, I also didn't want to bore people. This is the 6th or 7th time that I've explained to them.
Well, yeah, okay.